Okay, the midterms are graded, and you can look at them in Gradescope. If you have any, if you think we made a mistake grading the exam, you can ask for a regrade of specific problems in Gradescope as well. The solutions to the exam are posted in the schedule for the class under the entry for the midterm. PS7 is due this week. Kind of weird due dates because we didn't quite finish all into last week. And PS8 will come out this week and be due in 2 weeks after spring break. Any questions or problems about anything? Yes?
Normally Saturday is the late day cutoff, so will Sunday be the late day cutoff for the programming part of it?
Yeah. If you look at the Canvas listings for the problems, the cutoff date is listed. But yeah, I extended everything. The problems that I extended the cutoff date. Anything else? All right. I realize most of you have never seen the back end of Canvas of Gradescope, where we do grading. I just wanted to show you. It might change the way you take exams. This is how we grade. We're given, so we scan all the exams in, and I draw little boxes on the PDF to show Gradescope where to expect the answers to be. So essentially, I draw boxes on top of the, on the screen. I draw boxes on top of the boxes you see. So for problem 8.4, for example, Gradescope goes out and finds every answer that showed up in a box. And then we spend most of our time grouping the answers into sets that are equivalent. Gradescope does some of that for us. It uses machine vision techniques to group most of the answers, and we have to group the rest. So for example, the answer to this question was n log n, O of n log n. So this is what we see when we grade. We don't see names. We're not looking at anything around the boxes. We just see what you wrote in the box. Now, if we get curious, we can zoom out and look and see what you wrote in the box, outside. But for the most part, we're just looking at what you wrote in the box. So if what you do is write something in the box and cross it out and write the answer outside the box, that doesn't help us very much. Usually we'll get curious and look, but we don't necessarily look. So just be aware that it really matters that you put the answer where it's supposed to be, because that's really all we see when we're grading. All right, we were talking last time about prime numbers. And I haven't yet told you exactly why they're important. They're important in RSA, but we'll see that later today. I want to remind you what we talked about last time. So we were looking at the end at Fermat's little theorem from 400 years ago. Who remembers what that theorem says? Yes?
It was something like if the number is prime, then 1 mod n is 1 and 2 mod n is 1 and stuff like that. I don't.
Right. So we're talking about, let's let p be a prime. Then we've got the fact that a to the p minus 1 that's not what I want to do either. A to the p minus 1 is equivalent to 1 if you're working mod p, as long as 0 is less than a is less than p. And really all that matters is a can't be a multiple of p. It's true for any a unless a is a multiple of p. 2 examples are 0 and p are both multiples of p, so it doesn't work there. Every other case it does. So p can be any prime number whatsoever. You choose some number a, raise it to the p minus 1 power, mod p, you get 1. That works for all primes and for all a's except for the ones noted. But the converse is not true. Sometimes, if p is not prime, sometimes you'll get a 1, sometimes you won't. You can't count on it. Okay, now, let's look at an example. Let's take 5, for example. So what would this say about 3 and 5? So if we let p be 5 and we let a be 3, What's the theorem saying about 3 and 5 in this case?
Says that 3 to the 4 should be equivalent to 1 mod 5.
All right, 3 to the 4th should be equivalent to 1 mod 5. Okay, 3 to the 4th is 81. 81 mod 5 is 1. So that holds. The theorem predicts that'll hold, and it does hold. Now, one thing Fermat's little theorem gives you is an easy way to find multiplicative inverses modulo a prime. Can you tell me how to do that? What if I'd like to find the inverse of A mod P? So what I'd like is A inverse mod P. Yeah?
You could compute A to the P minus 2.
Okay.
That becomes A's.
Right, so if we know this, if we know that A to the P minus 1 is 1 mod P, we can rewrite that as A to the P minus 2 times A. That's just another way to write A to the P minus 1. That's going to be equal to 1 mod 5, or mod P. And we're multiplying A by this thing here and getting 1. So what does that say about this thing here?
It's equivalent to 1 mod P.
It's the inverse of A mod P. It's the thing we can multiply A by and get 1 back. So that's one consequence from Fermat's little theorem. Another consequence of Fermat's little theorem is it gives me another way to ask questions giving you what looks like an impossibly large exponent to simplify. Another way to reduce things to 1. All right, so if I said, okay, this is sort of a simple example. I do, some massive number, 2, 1, 5, 8, 7, 6 to the blah, 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 minus 1. And this is mod the same blah, 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 where the blah, blah, blah is prime. The answer is 1. So there are ways to, and I can pose questions to see if you can apply Fermat's little theorem to simplify things. And this is a couple ways to simplify things. One is recognizing A to the P minus 2 is always going to be an inverse if you're working mod P. And the other is if your exponent is 1 less than modulus, and the modulus is prime, then the result of the exponentiation is 1. Okay, so without using blah, blah, blahs, I could ask you, what's 7 to the 42nd power mod 43? I think 43 is prime. So you don't have to actually raise 7 to the 42nd power or do anything. You just notice Fermat's little theorem implies the answer here is 1. All right, well, let's put it, Fermat's little theorem, let's think about it some more. Let's find out where I left off. All right, at the very end, we're talking about how this theorem forms the basis of the probabilistic primality test that is used to generate prime numbers, to find random prime numbers. And it works like follows. We got some number n, and we're trying to decide if it's prime. So the first thing we do is we pick some a in the interval between 1 and n. So no point in picking 1 because we know 1 to any power is going to be 1. It's not a useful thing to pick. So we pick an a. We ask, is a to the n minus 1 power the same as 1, working mod n? And the answer is either yes or no. Now, if the answer is yes, what have we found out? We're trying to, do we know whether or not n is prime in that case? We picked a random a, we raised it to the n minus 1 power, took that mod in, we get back 1. What do we know? Yeah.
How do you know that it could be prime?
Well, we know it could be prime and it could be a composite, right? So we really don't know anything for sure. So we know it may be prime. On the other hand, if the answer is no, if it's not equal to 1, what do we know? We know it's not prime. So you can use that test to figure out if something is not prime. You pick a random a, and if it fails the test, the number is composite. But if it passes the test, it may or may not be composite. It may be prime, it may be composite. Nevertheless, that's the basis of the test. So let's see how that would work out. So we need to have an idea of how likely it is that if n is composite, it will fool the test. So here's some observations. First of all, n can fool the test if and only if a and n are relatively prime. Right? Why can't it fool the test if a and n, in this case, n is composite? Why won't it be able to fool the test if a and n are relatively prime? Why is that statement true? What if they're not relatively prime? The answer is there. Someone interpret it for me. Yeah.
If they're not relatively prime, then it wouldn't pass Fermat's test. Or no.
So the question is, okay, it says here, if a and n are not relatively prime, in other words, their GCD is not 1, then a has no modular multiplicative inverse, mod n. We know that from before. Two numbers have to be relatively prime for there to be an inverse. But what's that have to do with fooling the Fermat test? Yeah.
So it wouldn't be able to pass the Fermat test if it had no multiplicative inverse?
Well, but why?
Because a to the n minus 2 would be the multiple.
Exactly. So if we go back to this, if suppose p is not prime in this case, but if p is not prime, but nevertheless this turns out to be true for some a, that means that this is the inverse of a. Okay? If this equation is true, regardless of whether p is prime, if this equation happens to be true, a to the p minus 2 will be the inverse of a. In other words, there's an inverse of a mod n. But there can't be one unless a and p are relatively prime. So you're not going to get one out of the Fermat test if a and p are not relatively prime. Now, if p is prime, let me go back to the other slide. So in this test, if n is prime, of course it's going to be relatively prime to a. But if n is composite, it may or not be relatively prime to a. So first observation is no composite is going to fool the test all the time. It can only fool the test when a and n happen to be relatively prime. So that's one observation. Turns out there are some numbers that fool the test every time they can. They can't fool it every time, only when it's relatively prime. But numbers like 561, 1105, 1729, those are the first three Carmichael numbers. Carmichael numbers have the property that if n is a Carmichael number, then a to the n minus 1 will be 1 mod n every time that the GCD of a and n is 1. So it fools the test every time it possibly can. So Carmichael numbers would really foul up. Carmichael numbers are really good at posing as primes with respect to this test here. Another observation is, except for Carmichael numbers, every other composite number will fool the test at most half the time. Half the time it will fool it, half the time it won't. Or better than that. It might only fool it a quarter of the time or eighth of the time. But at worst, throughout the Carmichael numbers, no composite will fool the test more than half the time. Finally, there's a way to efficiently detect Carmichael numbers. We won't go into it, so we'll just ignore Carmichael numbers. We'll assume they don't exist. So put all this together, especially this bit, and what's a good probabilistic primality test? If you run the test and you get the answer yes, what's the probability that you just got fooled?
About 50%.
Yeah, it's at best 50% that you just got fooled. Could be better, but at worst it's 50%. I just said worst and best being the same thing, but hopefully you get what I mean. So we basically, we've got a 50-50 chance that we've been fooled. So we pick another A. Run it through the test. What if the answer comes back yes again? What's the probability that we've been fooled and this thing isn't really prime?
1/4.
Right? It's 1/4. We had a 50% chance of being fooled the first time, a a 50% chance of being fooled the second time. They're independent tests, different A's, so we multiply the probability. So we only got a 25% chance, a 1 in 4 chance that we were fooled both times. We repeat it again for a different A. Now we got a 1 in 8 chance. You can repeat that test as many times as you like. Let's say we repeat it 100 times. Each time we pick a different A, each time the answer is yes. At most, we have just been, the odds that we've been fooled, and this number really is prime, is 1 over 2 to the 100th. Minuscule. And you can keep going as long as you want to get confidence. And we talked at the very end of class last time of what you thought about that. What do you think about the fact that the process that generates the keys that are used in public key encryption depend on this algorithm and have a very small but finite chance of being wrong?
What's the worst that could happen?
Well, he says, what's the worst that could happen? Someone could steal your credit card. It's about the you know, that's typically, we're talking about e-commerce, that's what we're talking about. But the other thing is, what's the question I brought up last time is, yeah, there's a chance this might not work, but there are lots of other ways computers can go wrong that are far more likely. You know, a cosmic ray can literally flip a bit in memory and corrupt it that way. Lots of ways computers can fail that are far more likely than you've got a number that you think is prime that isn't.
Is the cosmic ray thing more likely than this?
Yes.
Wow.
Mainly because this is essentially impossible.
Right, yeah.
2 to the 100th is just really huge. Yeah.
I guess in practice, since isn't there like a polynomial time algorithm to determine if a number is prime? So once you find it,
there is a polynomial time algorithm to determine whether a number is prime.
so once you find a candidate, you can just run that on the candidate to.
Yeah, but that's not done in practice because this is good enough. The polynomial time algorithm is into the 6th. It ends a number of bits, and the number is just slow, and the numbers are long. So we just don't bother with it. In principle, we could, once we identify a good candidate, really make sure by running a really long-running algorithm, but this is judged good enough. Okay, so this sort of summarizes what we were saying. If you want to test a number as prime, you pick k random numbers between 1 and the number you're testing. Run that modular exponentiation for each one. And if it passes all the tests, you return true. If it fails one, you return false. So the complexity that's going to be of a modular exponentiation is n cubed, where n is the number of bits in the number. And you're doing k of them. So it's not a cheap, even that's not a very cheap operation, but it's fast enough for now. And that's what we talked about. Now, it turns out that saying that you got a 1/2 chance of fooling the test is vastly overstating things. Most numbers don't fail the test that often. And in fact, if you just chose your A's to be 2, 3, and 5, the first 3 prime numbers, and let k be 3, you would all be hard. If I told you to go out today and find a number with hundreds of bits that fools the test for those 3 primes, it'd take you a while. And these are jokingly called industrial strength prime numbers. You use a stronger test than this to determine whether something's probably prime. But that works amazingly well, just those 3 numbers right there. Yeah?
So if you randomly select numbers, what is the probability of one of them being prime?
That's a good question. So he's asking, okay, let me run with that question. So suppose I told you, find an n-bit prime number using this algorithm, how would you do it? What if I said, find me a 1,000-bit prime number? A random one, yeah.
Start with like all numbers, so where'd you go down like that?
Well, I want it to be random though. I want it to be so that two people running the same algorithm will probably come up with different primes. So we can't just start with, you can't say start counting here and up till you find one. Yeah?
But you just have to like generate 1,000 random bits and then run this test until you find one that.
Right. So you basically flip a coin 1,000 times to get 1,000 random bits. See if it's prime. If it's not, do it again. Keep generating random 1,000-bit sequences until you find a prime. And the question he asked was, how many times do you have to do that before one of them turns out to be prime? Right? If prime numbers are incredibly rare, you're going to be generating random numbers all day trying to find one that's prime. I'll answer that question when we put it off. It's coming up. Turns out they happen pretty frequently. They get less common as the numbers get longer, but they're still plentiful enough for our purposes. Right? And we already said this. Well, okay, I said it was coming up. It's coming up right now. So there's our algorithm, generate a random n-bit integer. Usually when we talk about an n-bit integer, we're assuming the first bit is a 1, right? And so the first, you only have to generate n minus 1 bits at random. You test it, you repeat. Now here's a theorem that always just blows me away to look at. I don't know how anyone could imagine this, let alone prove it, but Lagrange's prime number theorem. So let pi of x be the number of primes less than or equal to x. So what would pi of 10 be? 4. 2, 3, 5, and 7 are the only prime numbers less than 10. So pi of 10 is 4. Pi of 100 is, who knows, 15 or 20 or something. But anyway, in the limit, as x goes to infinity, pi of x goes to the limit x over the natural log of x.
Huh.
Why should that be? Why should...
Numbers. They do that. They
You
do
know,
like that.
I express this amazement every time I teach the class, but I've never taken the trouble to go and look at the proof, so that says something about me.
Are you just waiting for a student to prove it to you?
Yeah, maybe that's what I'm waiting for. Someone to come explain the proof to me. But anyway, so that gives us a way of estimating the probability of a number is prime. So here's how I'm going to work, how I'm going to do it. So I'm going to let x be 2 to the k. All right? Why am I picking 2 to the k? So like, if k is 3, that would be 8.
Because that's how bits work. That's how k-bit
Yeah.
integers work.
So every k-bit integer is less than 2 to the k. Right? 2 to the k, 2 to the third is 1, 0, 0, 0. So it's actually a 4-bit number. But everything less than that is a k-bit number. And then depending on whether you want to talk about all k-bit numbers or k-bit numbers that start with 1, there's a factor 2 here, but I'm just taking all k-bit numbers. Right? How many prime numbers are there less than 2 to the k? 2 to the k.
2 to the k over the natural log of k?
Well, yeah.
I mean, over the natural log of 2 to the k?
Yeah. So it's pi of 2 to the k, which is 2 to the k over the natural log of 2 to the k, roughly. Because remember, this is true in the limit. So the bigger x gets, the more accurate that estimate is. Let's see what I did here. I divided both sides by 2 to the k. Now, why did I do that? So this is how many prime numbers there are. What's 2 to the k? Yeah.
It's the total number of numbers.
That's how many k-bit numbers there are. So now this is the probability. This is sort of the fraction of prime numbers divided by all numbers. And that simplifies to 1 over the natural log of 2 to the k. Or it is 1 over the natural log of 2 to the k, which turns into 1 over k times the natural log of 2. Anyway, it's roughly 1.44 over k. And that's too hard for me, so I just remember it as 1 over k. So that means if you're looking for a 1,000-bit prime number, and you pick one at random, the odds that it's going to be prime are 1 over k. 1 over 1,000 in that case, roughly. And of course you can improve on that. You don't need to pick an even number. But ballpark estimate, just say 1 over the number of bits you're looking for. So for RSA today, you're looking for at least probably a couple thousand bit. I don't remember which is it.
Big.
Yeah, like 1024-bit prime numbers you're looking for. So you're going to have to test, about 500 before you expect to find them. Okay, so that's what I have to tell you about prime numbers. I keep insinuating that they're important to RSA, just as is modular exponentiation and modular multiplicative inverse and GCD and so on. Haven't really shown you why yet. We're about to turn to that. But before we turn to RSA, or encryption, I guess is what we're turning to, are there any questions I could answer about this? Okay. All right, so we're going to talk about cryptography, and it'll lead us to talking about RSA. And this is the general setup we're going to use. We're going to assume that Alice wants to communicate with Bob. These are sort of traditional names that are used in cryptography papers. And Alice has a message X that she wants to send to Bob. So Alice has some way of encoding. So she has some encoding algorithm. And so she, we'll call that E here. She encodes X with the algorithm E and gets X prime. She sends those bits over the network. Bob has a decoding algorithm, which we'll call D, and turns X prime back into X. That's just a block diagram with encryption. And then the other player in the middle is Eve, who's an eavesdropper. We assume that she can intercept the bits and that she knows the algorithm that Alice and Bob are using. That's not a secret. And we'll always be wondering, okay, how can Eve contrive to figure out what the message is, what X is, given X prime and the algorithm we're using. Well, let me show you a couple simple encryption algorithms. First one is called a Caesar cipher, supposedly used by Caesar. And this is an example from a geocaching webpage. So geocaching, you get the coordinates of something hidden in the woods or in the city, and you got to go find it. Sometimes it's hidden cleverly, or it's there are a lot of places to look, and so hints are given. So this is the encrypted hint you'd find on the web page for a cache. Okay, and the encryption that's used is called ROT13. So basically, this is saying A maps to N, B maps to O, C maps to P, or vice versa. N maps to A. So what would be this word right here, BS?
That's OF.
OF. Okay? So it's not a very good algorithm. Why is it called, where's the 13 come from in the name? Yeah.
Isn't it like rotate everything by like 13 letters?
Rotate by 13. Basically, if you think of A as being 0 and B as being 1, we're adding 13 mod 26 to get so add 13 to A, you get N. Add 13 to O, you wrap around and go back to B. So really the key, the secret here is just a number. In this case it's 13, it's an open secret. This isn't meant to be secure, it's just meant so you have to click on the link in order to see what it says. And most people that look at these forms get pretty good at just, there's certain words that are easy to read because you see them so many times in that form. This one says, let's see what this one says. You know, like that FVQR, you see West a lot in these hints. So that's Caesar cipher. Easy or hard to crack if you don't know the, in this case it's 13, but you could rotate by any number. All right, there are just 26 things to try.
Yeah.
So you just try all the rotations and see which one produces something that makes sense. Okay? Then there's substitution ciphers. In a substitution cipher, what you do is you replace, you map every letter to a randomly to another letter, but there's no pattern to it. So this is the crypto quote puzzle from the Tribune. My wife does them every morning, and I just went and took a picture of hers this morning. So how does she go about cracking it? What you see is all she has to go on. Yeah.
You can use certain language characteristics, so E is the most common letter in English language.
Okay, so she knows that E is the most common letter. What else? Yeah?
You could find like commonly used like small words that repeat itself over and over again.
Okay, so the is a pretty common word.
Like,
You know, is. She sometimes explains to me about the little tricks she's learned. And she even has a sheet she keeps around, maybe all 2-letter words or something like that. But she's really good at this. She does it in a few minutes usually. Notice she didn't get 1 letter because this name right here. Anyone know what that is? So anyway, the key would be something like this. It would say, okay, to encrypt a plain text, encrypt an F, replace it with a C. To replace an N, replace it to a V. And these blanks are here because not every letter is represented, right? So I would only been guessing if I'd give
I
you
think it's an A.
Think it's what?
An A.
An A? Okay, I'll let her know.
Because I looked up Pietro and the first result was Pietro Aretino.
Yeah. So that's the substitution cipher. And this is a little harder to crack, but it's not secure by any means. And another property of the substitution cipher, cracking it, is if I only gave you 1 letter and said this is encrypted using a substitution cipher, would you have any hope of cracking it?
No.
You know that the plain text was 1 of 26 letters, but that's all you know. Any of those 26 letters is equally likely. On the other hand, what if I give you 1,000 letters and tell you it's an English word? It's an English, not a word, an English passage. Is the longer the message becomes, the easier it is to crack, just because you've got more clues to go on. You know, the distribution, the frequency distribution of the different letters will settle down into their actual frequencies in English, and you'll get the a lot of times. So the longer these messages get, the easier they are to crack. And that brings us to what you can think of as a substitution cipher, a one-time pad. It is absolutely, positively uncrackable, but not used in practice, which seems kind of weird. But let's explain what it is, why it's uncrackable, and why it's not used in practice. So the idea is to send an n-bit message. Alice and Bob must agree on a random n-bit key, R. Okay? And then all they do is what Alice does is takes plain text message and XORs every bit with the corresponding bit in R. And Bob decrypts by taking the encrypted message and XORing it again with R. Okay? So that's called a one-time pad. So here's an example. So there's X, sequence of bits. There's a randomly chosen R. And if we XOR, you see we get, okay, 1 XORed with 1 is 0. So we just get a 1 when the 2 bits differ. So they differ here, we get a 1. They're the same here, we get a 0. Now, why do I call this a kind of a substitution cipher? Or I might even call it a Caesar cipher. What sense is it either? Yeah?
You can kind of like go both ways.
Say again?
You can go both ways. Like you X or R, you'll get like the encrypted version, and if you do the same thing, it'll go back to the original version.
Sure, it has that property. Yeah.
Each bit masks like the original bit.
Yeah. Basically, each bit is encrypted. This is like a substitution cipher for I guess it's more like a Caesar cipher. It's like a Caesar cipher where we use a different key for each bit. The way we encrypt the first bit has nothing to do with the way we encrypt the second bit. They're completely independent. So basically you can think of what this tells us is, okay, we're going to use a Caesar cipher where you rotate by 1 for the first bit. Then we're going to use a Caesar cipher where you rotate by 0 for the second bit. And then a Caesar cipher that rotates by 1 for the third bit, and so on. So we're using a different rotation, either 0 or 1 for each bit. And that rotation is randomly chosen. So figuring out what one bit is doesn't tell you anything about what the previous bit or the following bit is. They're all independent. So then if we, just to undo the process, you'll notice I put X on here again. So if you XOR R and X prime, again, you recover the original message. Sort of cancel out. So that's a one-time pad. But you can't use a key twice. What happens if you use a key twice? Yeah?
It becomes a 2-time pad, and we can use that to decrypt the first message.
Okay, so it becomes a 2-time pad. We can use it to decrypt the first message. Basically, the security of this depends on the fact that every bit is encrypted independently of every other bit. If you reuse it for a second message, now you've got, there's interference. There's a correspondence between the two messages. There are a couple ways to look at it. Here's one way. If I encrypt X using R and I encrypt Y using R, then if I XOR the two encrypted messages, X prime and Y prime, it turns out it simplifies to X XORed with Y. So now the element of randomness has gone away completely. Now what you have to look at is one plain text message XORed with another plain text message. And that's a whole different ballgame. They're not independent of, there's no randomness involved anymore. The other way to think about it is this. Suppose I gave you a 1,000-bit message and you knew it was English. And it was encrypted with a 1,000-bit one-time pad. Okay? You could start generating 1,000-bit keys at random and seeing which ones produced 1,000 bits of English. But what would be the problem with trying to break the code that way? Yeah?
Take a while. If you were able to decode like one bit that doesn't give you any information about the other bits. So like if you were to decrypt one word, you might be able to use that.
Right, but what I'm saying is we're going to decrypt, we're going to pick a bit sequence at random, a key at random, and attempt to decrypt it, see if it decrypts to English. Okay? So suppose we find a way to decrypt it to English. Haven't we cracked the code? Yeah?
No, because you can decrypt it into any English.
Right. There will be a key for any, you give me a 1,000-bit encrypted message, 1,000 random bits. For any 1,000-bit English passage, there will be a key that decrypts that thing to that English. So all you can find out by generating random keys is the same thing in you going in. The thing that was encrypted is 1,000 bits of English. It's one of the massive number of 1,000 bits of English that are out there. And I haven't even mentioned the fact that it's not practical to generate 2 to the 1,000 different keys and try them all out. Now, suppose though that you have 2 messages, one encrypted, 1,000-bit English passage encrypted with one key, and then another one encrypted with the same key. Now what happens if you find the key that decrypts both?
You get the passage.
That's very likely to be the original passage. It's unlikely the same key will decrypt 2 random strings to multiple English passages. Well, I'm not saying that quite right, but okay. If we've just got X and R, or X prime and R, you don't know R. There's a key that will generate the original X. There are other keys that are in every other possible original X. If you're talking about English passages, the original X will find a way to decrypt any possible original English passage. We'll also find lots of keys that generate the gibberish. If you have 2 things encrypted using the same key, then the probability that they both happen to decrypt to the same English, and that English isn't the original, is very small. So anyway, you don't want to reuse the key. So what is the problem with the one-time pad? It's perfect, it's very efficient, but it's not used in practice. Yeah?
The length of the key has to be the same as the message.
Well, the length of the key has to be the same as the message. That's one thing, but that's not the real killer. Yeah?
Is it that you can't like securely communicate what the R is to the decoder without sending it over, and in this case, Eve could get
Right.
that too?
The problem is Alice and Bob have to agree on the key. And how do you get the key from Alice to Bob? Encrypt it? Yeah?
Couldn't you just prepend it to every message that you send? Like, well, never mind, because then it would be the same size.
Yeah. Now, I say it's not used in practice, but in fact, it used to be used in practice. One-time pads were used in the Cold War, say for encrypting cables from Washington to Moscow. And when I say one-time pad in that instance, I don't mean that they weren't using bits. Basically, you could think of a one-time pad as being a sequence of numbers, and each number was the amount of Caesar cipher rotation to apply to a character. So you might encrypt the first character with a rotation of 1, the next one with 5, the next one with 16. And so a key would just be a sequence of random numbers between 0 and 25. Okay? And when you sent a message, you would have to say, okay, you have to agree on the key you're using, and you only use each key once. So how did they handle the key transfer problem?
Human messenger.
Yeah. Human messenger. The proverbial briefcase on the diplomatic representative handcuffed to the wrist, containing the code book that was just full of random numbers. And then if I want to communicate with you, I say, okay, I'm using code 3. You'd use it, and you'd never use code 3 again. When you'd used up all the keys in the book, you'd have to send a new book. So one-time pad, that's how that was used. And of course, if someone intercepted the code book, then all the messages could be read. I have seen proposals that the idea that you could actually securely transmit random bit sequences, one-time pad keys, over an open network completely unencrypted, using quantum techniques, which would mean that if someone intercepted it, you would know. Okay, I don't know how to explain it further than that. Seems like as long as you call it quantum, you can you can propose any kind of weird behavior. But the actual act of reading the key, someone intercepting the key would change it, and you would know it had been read. But that hasn't happened yet. Yeah, so those are our two problems. The key has to be the same length as the message, and we've got to transmit the keys. All right, let's take a quick break, and we'll talk about what's actually used in practice. prior to 2001, from about the 60s into 2001, or maybe the 70s it was, I don't remember. There was something called the Digital Encryption Standard, DES, D-E-S, and it was replaced in 2001 by AES. So DES was an encryption standard that was developed by IBM and the National Security Agency and given to the rest of us to use. Now, if you're of a suspicious nature, why might you be suspicious of those two organizations saying, here, encrypt your data using this method?
You're going to say, we'd love to have a backdoor into your phone.
Right. The NSA's job is to, their official job is to read, is to break encryption from other countries. They're not supposed to do it domestically. We can wonder about whether that happens or not.
Well, don't have to, we know.
And IBM, you know, I don't know what your impression of IBM is today, but back in the 60s, IBM was like if you rolled together Facebook and Amazon and Microsoft and Google. I mean, they were basically
the bad guys.
Yeah. So, plus, okay, so people were suspicious of the code for that reason, that it probably had a backdoor into it. But in any event, it became obsolete as computers got faster, and it was replaced by this this new standard, which was produced via an open competition in 2001. So this is how I'm not going to explain the theory behind AES. I'm just going to show you how it works. To use AES, Alice and Bob have to agree on the key. It's not a arbitrary length key. It's a fixed length key, but they both have to hold of this key, and then the encryption algorithm encrypts, the decryption algorithm decrypts, but they both have to have as input the same key. And that key is 256 bits long. And to encrypt, what they have to do is break the message into 256-bit blocks, and then encrypt each block separately and send them sequentially. So every chunk is an encrypted. 256 bits are encrypted into 256 bits. Now, this wouldn't work if you're using one-time pad, because we'd be reusing the same key each time, and we already said that wasn't secure. But AES is designed in a way that it's at least believed to be secure. And the way to think about this is, when you encrypt, the 256 bits that you're encrypting, you can think of that as a 256-bit number. And this key K and the algorithm E have the property, they just map every 256-bit number to a different 256-bit number. Not by building a gigantic table, like the one I showed you for my wife's puzzle, but by computing it each time. So really, this is a substitution cipher. It's just that rather than substitute letters for letters, it's substituting 256-bit numbers for 256-bit numbers. So how would you attack this if you didn't know the key? What would Eve have to do to break the code? What's the obvious way? Yeah?
Try every 256-bit number and see what makes sense.
Well, yeah, try every key. Take a key, decrypt, and see if what you got makes sense. And the fact that there are multiple blocks makes it unlikely. It makes it very likely that if you guess a key that decrypts all the blocks into something that makes sense, that's likely to be the answer. Just because if there's only one block to decrypt, it's going to be harder. In fact, if there's only one block to decrypt, you won't be able to reliably say what the answer is, because lots of keys will decrypt it to something that makes sense. But if you got multiple blocks in the message, you can eventually guess it. But what makes this not practical to do?
Takes too long.
Yeah, it just takes too long. Too many keys to sift through. Now, with enough computers running in parallel, you could crank on it and perhaps crack it, but you've only cracked it, cracked one thing, one social security number, or one credit card number, and it'd be very expensive to do. But as computers get faster, it becomes a worry. And D just knows, the D algorithm reverses the mapping. So conceptually, you just got a giant substitution cipher. The key's designed to be reusable. And the term for this is a symmetric block cipher. So it's a block cipher because you're encrypting blocks of bits. It's symmetric because both sides use the same key. So this sounds pretty good. What's the problem with it?
What happens if somebody gets their hands on the key?
Well, if someone gets their hand on the key, we're sunk. And that's the root of the problem. Yeah?
Both sides have to have access to the key.
Right. It's the same as the one-time pay. We've somehow got to communicate the key. If you want to send your credit card number to Amazon.com and you want to encrypt it with AES, somehow we've got to agree on what key to use in a way that Eve can't intercept. So that's the problem. So we'll come back to that problem. Next algorithm is RSA. It's named after the inventors, Rivest, Shamir, Edelman. They invented it in 1977. And they, as soon as they started publishing about this algorithm, the United States federal government began active efforts to suppress the research. They tried to forbid publishing about it without, first they tried to forbid publishing without their approval. The NSA wanted papers about RSA to be submitted to them, and they would say yes or no. Could it be published? That didn't work. Then they tried to compromise. The RSA would at least get to look at it first before it was published, even if they couldn't say yes or no. That didn't fly. Congress passed a law forbidding the export of software containing RSA technology of a certain bit length, a certain strength, from the United States. And that stayed into effect until almost the year 2000. What was the US government so worried about? Yeah?
It's really hard to break it?
Yeah, they were,
We didn't.
right, they didn't know how to crack RSA. Their job is to crack codes. They didn't want foreign governments, or perhaps US citizens, being able to encrypt things that they couldn't read. Why did they drop their opposition at the end of the century?
Cold War ended.
Well, yeah, the Cold War ended, but what were you going to say? Some people suspect that the NSA cracked RSA. And then they say, oh yeah, you go ahead and use it. Personally, I think it's unlikely because surely we would have found out about it by now. That's a big secret to have to keep all those years. But the bottom line is the export controls weren't working because even if you could keep software containing RSA from being exported to the U.S., other countries have programmers. They can create software too. So it was just what it was doing was just hurting the U.S. software industry. So anyway, that's a brief history of RSA. The way they did it was they classified RSA as a weapon of war. So the same way that you can't export a tank from the United States without a license. Same thing with this encryption. So here's the block diagram of how RSA works. If Bob wants to be in the business of receiving encrypted messages, he has to create a public key and a secret key, a key pair. So Bob needs two keys, a public key and a private key. And it's the receiver that has to have these keys. The public key is designed so you can publish it in the phone book. You can put it on your web page. You may have seen some people put their RSA keys on web page, in their web page or in an email footer or something like that. So it's public. So to send a message, Alice needs to go to the public key, but does not need to go to the secret key, the private key. So only Bob knows the secret.
Is this what SSH is built on? With its keys? Is this what SSH works from?
Yeah, SSH would.
Okay.
It's part of it. Keys are usually pretty long. Nowadays, 2048 bits or more. In the past, they were shorter. But as computers get faster, the bit lengths have to get longer. And it's like a substitution cipher where we encrypt. What Alice does is she encrypts using the public key. And that maps every number in the range to a different number in the range. AES does the same thing in a different way. So it's a substitution cipher at the block level. So Alice runs the encryption algorithm using the public key, and then Bob decrypts using the secret key. So you can't decrypt. You can encrypt using the public key. You cannot decrypt using the public key. You have to have the secret key to decrypt. So what problem does that solve?
The sharing key.
Yeah, the key transmission problem is solved because the only thing Bob needs to share is the public key, and the public key is designed to be public. It doesn't have to be kept secret. So you can tell everyone, you can broadcast it. It turns out, and this will come in useful later, we can take X, encrypt with the public key, and decrypt with the secret key and get the answer back. Or we can take X and encrypt with the secret key and then decrypt with the public key. And that may seem kind of weird, but we'll invent a use for it here in a bit. Now, we're going to assume that Eve knows the public key. Eve knows Bob's public key. And as far as is known, that doesn't help her break the cipher. So we're going to assume Eve knows what algorithm is being used. Eve knows Bob's public key. Eve intercepts X prime. It is believed, and I keep saying it is believed because we don't know for sure, but it is believed that there is that there's no practical way to crack even given all that information. I'll have more to say about that later. So this is not a symmetric block cipher, it's a public key block cipher. And the problem with it is it's inefficient. The step that does the encryption is actually a modular exponentiation, and that's an n-cubed algorithm. And it turns out to keep this secure, as computers get faster, the bit lengths get longer, which means that n-cubed becomes more and more significant. So in fact, what's done in practice, and I have a lot more to say about this later, is that we don't use pure RSA or pure AES. We use both in combination. Can you think of a way to combine the two to eliminate their problems? Yeah.
Use RSA to exchange a key.
Right. Use RSA to exchange the keys. So basically, if Alice wants to communicate with Bob, they use AES. But first, they have to agree on the key. So one of them generates a random key to use for AES and transmits it using RSA. Then both sides have that key. Then they can use the more efficient AES to actually do the communication. And every time anyone communicates, you can just generate an AES key at random and use it. But the cool thing about RSA is it's easy to understand how it works. Because we have been laying the groundwork over what seems like a month of having one lecture a week on the topic. And we're finally here at the payoff. So here's how RSA works. You first select two distinct primes, two primes that are different, P and Q. And nowadays they need to be at least 1,024 bits apiece. 10, 20 years ago, used shorter ones, like 512-bit primes, but they aren't long enough anymore. You multiply them together, and that's called the modulus. N is the modulus. N is the product of two primes. Then you compute this number phi, which is just P minus 1 times Q minus 1. So far, the only algorithm that we've studied, that we've used, is prime number generation, and I guess multiplication. Multiplying long, gigantic bit streams. Okay, then you pick a small integer e such that the GCD of e and phi is equal to 1. So there's our GCD algorithm. So basically, you just go through some small integers till you find one that works. Then you choose D, another integer d, such that e times d is 1 mod phi. In other words, their inverse is mod phi. So what algorithm would we use there?
The multiplicity of inverse one.
The modular multiplicative inverse algorithm. Okay, so we have the modulus n, we have the public exponent e, we have the private exponent d. The public key is the combination of e and n, and the private key is the combination of d and n. So we can tell the world e and we can tell the world n, but we got to keep d a secret. Now, if you could factor large numbers efficiently, this whole thing comes tumbling down.
Yeah.
Okay? How could you use a factoring algorithm to attack RSA?
Well, if you could factor.
Let me get that answer back there.
Yeah. If you can just start trying those prime numbers p and q, if you figure out what p and q are, you can derive e and d.
All right. So if you can figure out what p and q were used, you can just regenerate. You can find the rest. You know what e is. You can find d. So how do you find out what p and q are?
Factor in.
Factor in. N is in the public key. So the security of RSA hinges on the assumption that there is no way to factor large numbers in any reasonable amount of time. But no one has proven that it is, in fact, that you can't factor large numbers in public efficiently. It is, no one has ever found an algorithm to do it. Lots of people have looked.
Wow.
If you found one, you could either be famous or sort of a rich criminal. Or you might be a target. I'm not sure. You'd be in a weird spot because as soon as that algorithm is published, e-commerce collapses until they can replace all the browsers and all the software with a different encryption strategy, which they have one that would work, but it's not rolled out. So I don't know what it would be. It'd be very dramatic.
Weird ethical spot.
Yeah. Yeah.
Is it harder to factor a prime number, like a big prime number, than like a negative plus number?
Well, okay. So some numbers are easier to factor than others. If the number is even, yeah, it's easy to factor. If the factors are small, you can find them by iterating through numbers. N is going to be hard to factor just because it's two gigantic prime numbers, each hundreds of bits long. So it's just sort of trying all the possibilities isn't going to cut it. Yeah?
You mentioned that they have like a replacement algorithm that they would use to replace this. If they ever...
It's called elliptic curve encryption. It could replace this. I'm not sure why it hasn't. I guess because what they have works so well right now. But how fast could they roll out brand new browsers for everybody and brand new websites? So you have to replace code of some of the websites. You gotta think people have thought about this. But. All right, and yeah.
So with that one, have they proven that the elliptic curve encryption can't?
I'm not sure about that. Yeah, I'm not sure exactly what's proven on elliptic curve. The actual encryption is simple. You take a block of bits, raise it to the power e, e being the public exponent, mod a single modular exponentiation. Decrypting is the same thing, except you take the encrypted message, raise it to the power d mod n. So it's a single modular exponentiation for each block. And the length of the block is governed by the length of the key. The thing you're encrypting has to be a number less than n. So that's all our algorithms in use now for RSA. So here's an example. We'll let P be 3 and Q be 11. So what would N be? N would be 33. Phi would be 2 times 10. That's 20. Okay, then we got to find a small e. So what's the smallest e that is relatively prime to 20? 3. 2 doesn't work, but 3 does. Now we got to find the inverse of 3 mod 20. 7. 7 times 3 is 21. That's 1 mod 20. And now the public key is that combination of the 3 and the 33, the public exponent and the modulus. There's the secret key. Okay? Of course, this would be easy to crack. This would be easy to crack. If someone said, there's the public key, I bet you can't find the secret key, they'd be wrong, because you would factor 33 in an instant, get 3 and 11, and repeat this calculation. So there are lots of ways to attack RSA that have been tried. What's believed is there is no better way than factoring the number, and that is assumed to be hard. So here's just shows you a few ways that you can do the encryption. So one thing is that 0 and 1 encrypt to 0 and 1. So you probably don't want your message to be all zeros or all ones. You can compress or something. Not all ones, a single one. But anyway, 2 maps to 8, 3 maps to 27. That's easy to see. We haven't gotten bigger than 33 yet, so the modulus has no effect. 4 goes to 31, 5 goes to 26, and so on. And over there's the inverse operation. Turns out there's always one in the middle somewhere that encrypts to itself. That's just a property of this. But it's extremely unlikely that you would ever encrypt something like that. So RSA can be used in several forms. So you can encrypt with the public key and decrypt with the private key. And that's called encryption and decryption. That's what we usually think of when we think about RSA. So it's used for security. Anyone can encrypt as long as they know your public key. But only the private key holder can decrypt. And generally, it's not the people that have browsers that have RSA keys. It's the corporations, the e-commerce folks. So Amazon has RSA public key, private key pair. The browser doesn't have to have them. But there's a way to turn it around where you encrypt with the private key and decrypt with the public key. And that's called signing and verification. So suppose I took some document and encrypted with my private key. What good would that be? Anyone could read it, right? Yeah?
It proves that you're the owner of the document.
Right. It proves that I'm the owner of the document, that I originally encrypted this thing. So one thing I could do, if I go home today and invent a fast factoring algorithm, I can write the algorithm on paper, or just put it into a PDF, and I can then sign it, encrypt it with my private key, and then publish it in a newspaper. And then in the future, if anyone claims they invented my algorithm, I could say, no, I invented this algorithm because, look, I encrypted it with a private key, and here's the public key that decrypts it. The fact that it decrypts with my public key means that I'm the one that encrypted it in the first place. So that's called signing and verification. So it's used for authentication. If something decrypts with someone's public key, it means it had to be encrypted with their private keys. As long as the private key was kept secret, only they could have encrypted it. Only they could have signed it. Utah was the first government in the world to accept digitally signed documents signed digitally like this, legally. And they established an entire office in the government to manage. You had to deposit your keys with them, and no one used it, so they repealed the law. But Utah did have that distinction for a while. Okay, this, I'm going to skip over this. It's a proof. It's the proof that RSA works. It turns out it's not a hard proof, but there's other things I'd rather talk about right now. I may decide to come back to this next time. But if you're at all interested, I encourage you to look at it because The steps are all easy to follow. You just got, it depends on Fermat's little theorem, it depends on those properties right there. And it shows you why it works. But I want to talk about vulnerabilities, factoring the modulus. So there's a business called RSA Labs that promotes RSA, and they created a series of challenges years ago, I don't know, probably 20 years ago or more, of RSA moduli, ever longer. And they had cash prizes associated with each one. So they would say, here's an RSA modulus, crack it and you get $5,000. So it's sort of a challenge to the community to see how good we could get it factored. The largest one that was ever factored was RSA 768. So a 768-bit number that was a product of 2 primes, 232 digits. By the time this was cracked, they had rescinded their offer. They weren't giving the award anymore. Either because I don't know what their motivation was. This was done in 2009. So at the time, the standard bit length for an RSA modulus was 1,024 bits. So this wasn't quite there yet, but it was getting close. But look what it took. It was an international effort. Step 1 took 6 months on 80 processors. So they're using, they're doing something more advanced than just trying every possible factor. So they're using the best known algorithm. 6 months for the pre-processing step. Step 2 took 2 years on many hundreds of machines, the equivalent of 1,500 years on a single core deep 2 gigahertz processor. Okay, so it either takes a very long time or a lot of hardware. And they predicted that just with the speed up of computers, well, I don't know if they're really speeding up anymore, but anyway, they predicted that the standard 1,024-bit at the time RSA modulus would be factorable by the year 2020, which here we are. And no one has yet factored it, at least published that they factored the 1,024-bit number, because there is one, there's an RSA number still out there of that length. Maybe it's just because it's just not worth it. It's too expensive. The government, or I don't know whose government, but anyway, whoever makes recommendations about the internet recommended that the 1,024-bit moduli be phased out, and they have been. So that just shows you that was the state of the art 11 years ago. Takes a lot of effort to crack one of these. But there are other vulnerabilities that RSA have shown. Let me explain one of them to you. So in 2012, some researchers in Switzerland went out on the internet and found all the RSA keys they could. They just sucked them up, all the public keys they could. Those public keys are public. So they accumulated 7.1 million of them. They found that 27,000 of them offered no security at all. A small percentage, but still a large number. And let me explain what I mean by no security at all. What they found was they'd go to this website and grab a public key. And they go to this website and grab a public key. And they would discover that one public key was a product of P and Q1, and the other public key was a product of the same P and a different Q. And how did they determine this if it's hard to factor numbers?
GCD and 1 and 2.
Right. Just by doing a GCD. They got 7.1 million keys, and then they took every pair and took the GCD of every pair. And if it happens that there's a factor shared between 2 of the keys, the GCD is going to be that shared factor. Now, what do you suppose is the correct way to generate an RSA key? It needs to be different from anyone else, and it needs to be using a pair of prime numbers no one else has ever used. So how do you do that? Yeah?
Generate 2 random prime numbers.
You've got to generate 2 random prime numbers, but you've got to do it securely. The thing about the standard random number generators that you use in programming languages is they're not cryptographically secure. They're really not random number generators. They're pseudo-random generators, and they follow a pattern, a repeating pattern. They have to be seeded, but if you know the seed, which is sort of the starting point, it's completely deterministic. People have used that property to attack like online poker sites, figuring out random number they're generating and being able to predict the cards to some extent. So it turned out that this was due to faulty key generation. The random number generators that were used to generate the prime numbers were not sufficiently random. There was a pattern to them, and it turned out then that multiple sites independently had to produce the same pair of prime numbers, which ought to be almost impossible. If it means the same coin flip came up, for every bit. So it should be virtually impossible, but it wasn't. It was limited almost entirely it wasn't like e-commerce websites, it was embedded systems. Pieces of hardware running encryption. So the problems, the weaknesses of RSA to date have all proven to be sort of implementation mistakes. Just screw-ups by programmers. All right, so where we'll pick up next time and finish next time is I'll show you briefly exactly how, or abstractly how, AES and RSA are used in e-commerce.